It's my great pleasure to host the seminar speaker at this time, Professor Gyuwon Lee. He is from Kyungpook National University, South Korea. I know Gyuwon since almost like 15 years at least. We met first, we overlapped, or at least we collaborated a little bit when I was in McGill University, where he actually graduated in 2003 with specialization in radar meteorology and ice microphysics in general microphysics. He's currently a professor of atmospheric science at the School of Earth System Science, and he's also the director of the Center for Atmospheric Remote Sensing Research. Before that, he was a research scientist at NCAR, and he was also a radar scientist at the Marshall Radar Observatory in McGill University soon after he graduated. His expertise is on quantitative precipitation estimation, forecasting, precipitation microphysics, instrumentation development, mesoscale meteorology, and field experimentation. He's been awarded the Presidential Award from the Korean government and the Moksan Award from the Korean Meteorological Society for his service in the community. And he's also a member of the WMO in the working group on nowcasting and mesoscale research. And he's been in New York for almost 2 months. He has visited us a couple of times, and he has visited many other places that you can imagine a lot of people in the US and Canada also. He just came from Canada, would be interested in his research. And it's with great pleasure to introduce him. He's going to be talking to us about ice generation processes. I'm pretty sure it will be very interesting. And thank you very much for coming. Thank you.
Thank you for such a comprehensive introduction. I didn't know NASA had that information actually. So I'm Gyuwon Lee. So I'm working in the Kyungpook National University. My university is located a little bit southeastern part of South Korea. So the South Korea is the very period of very turmoil. The political situation now. But we hope it starts soon. So I will talk about a little bit on the ice generation processes. It's mostly based on the remote sensing. So since I'm expert in the weather radar and LiDAR, so I'll talk about how we can actually identify ice generation process with the weather radar observation. And also Pablo was mentioned about I'm the director of Center for Atmospheric Remote Sensing. So that was sort of very interesting arrangement with operational agency like Korean Meteorological Administration. We set up the research center and we do the continuous collaboration. It's almost the 12 years of collaboration with the operational center. So that give us a lot of chance to promote our research as well as send our students to the operational research center, and they build up the new research group there too. So first part, I will talk about some collaboration with the KMA, and then later part, I will talk about the ice microphysics. So let me introduce a little bit short history of radar meteorology in Korea. So the first Korean weather radar was S-band conventional radar in the Seoul area. So we had only single S-band radar and covering entire Korean peninsula. They measuring up to almost the 600-kilometer range. So it was a sort of the first radar we studied. And then they replaced this radar many times. Now we have a full radar network of S-band dual parametric radar that are complete in 2019. So as explained, we started with S-band in 1969, and then we switched into the 5 C-band Doppler radar network in between 88 and 92. So in that way, we can build up some network of weather radar. And then we went through the third phase. So we went back to the S-band parametric weather radar and combination with the 2 C-band radar, Doppler radar network up to 2010. And then a lot of new things happened when I went back to Korea. I went back to Korea in 2008. So that's the period actually the radar meteorology in Korea was actually the start. It's a new era for the dual polarimetry. So during this period, a lot of things happened. So actually, we had the so-called the vice administrator, the foreign vice administrator in KMA. So the Ken Crawford, some of you may know the Ken Crawford from the University of Oklahoma. So he came to Korea to KMA and took a vice administrator job. And first thing what he did is, revolutionize observational network. So first topic was weather radar system. So he built up the weather radar center. So it's now about 60 people working in the weather radar center. It's very similar to the US weather radar center. So they actually operate and do the analysis. They do a lot of research related to weather radar and also the operation too. And then in Korea, we have the three agencies own their own weather radar network. So the Ministry of the Korean Air Force and Ministry of Environment that is responsible for the flood forecasting, and also the Korean Meteorological Administration. They are the three agencies actually working on the weather radar network. So before that, they didn't talk much. So, but through this process, they had the agreement. So they will share data in real time, and also they will do the research together, and also they will operate radar together too. So there was a big change. So it's basically, with the 11 radar or 10 radar, it become, 27 radar over Korean Peninsula. And then to build up the technology transfer was to test some ideas. So they built up the weather radar test in 2010. And then they also realized the importance of collaborative research with academia. So I was there, so they came up to me and they want to build up the cooperative center for the weather radar research. That happened in 2012. So and then they complete the 11 S-band dual parametric radar system. So it's keep working now. So this is the multi-agency agreement in 2012. And then they had the agreement, and then they start to share radar data and do the research all together. So as mentioned, the KMA operating weather radar, and also the Korean Air Force, it's similar to the TDWR, and it's mostly C-band radar, and also flood control office. They are responsible for the flood forecasting, and so they built a completely new weather radar network in starting from 2009. And then in academia, we built up the collaborative research center. So when they started the multi-agency agreement, there are a couple of questions. But one of the most important questions is they want to improve accuracy in radar data by using multi-radar system. And also they want to improve the QPE, quantity precipitation estimate, and also dynamic field that coming from the weather radar, and also of course data quality. And by adding the three agency weather radar in coverage, improve the radar coverage. I will show a little bit later. And also they want to use this data to improve the monitoring and the forecasting capability of a weather system too. So this is an example of what happens. So this KMA radar network, we do the simulation to indicate what will be the lowest observable height for given location. So the blue color is basically we can measure at a lower height. But if you go to the red and the blacks, then you cannot get any information in the lower layer. So you have the radar beam actually overshooting. So with the only KMA radar, so you have the good coverage over the coastal region because they are responsible for the monitoring weather radar system coming from the far distance. So that's why they put up the most of the radar in the coastal region. And then the Korean Air Force, they don't care about what's happening in the entire Korean Peninsula. They just setting up their radar in the airbase, and they monitor the weather around the airbase to give us some information to the aircraft. So that's what you see in the place where you have the airbase. You see the pretty good coverage. but within maybe 30 kilometer or 40 kilometer. Beyond that, you don't get much information with the C-band polarimetric radar system. This is from the flood control office, new radar network. So they are responsible for the getting the accurate precipitation information over the land. So that's why they put the most of radar in inland. So we have 6 radar. So and then we now start to combine all those data simultaneously. So that's what you see. For the entire Korean Peninsula, you have a radar reflectivity or radar measurement below 1 kilometer. So it's a sort of a complete different concept. So if you look around the US radar network, next radar system, it's pretty hard to get the information even below 2 kilometers because two radar are far distance. So they have been overshooting, and in between radar, you don't get any information. So basically, you are lack of observation in the lower layer. But our radar network it's pretty good, So we get the boundary layer information as well as the 3D information in very detail. Let's look at what's happening in the 1 kilometer with the only KMA radar. So you have a lot of the blank area, so that doesn't collect any radar data. But if you combine the 3 agency weather radar, so even at 1 kilometer, we have a couple of places that has a radar get collected at least 5. So the 5 or 6 radar can provide the radar data at the single location. So that means you can use the overlap information to improve data quality too, or the accuracy of your analysis. And even if you go to the 3 kilometer, so now it will become much better. So some area you have a radar over 13 or 14. So now what happened is the KMA actually by combining all this data radar, KMA is the first one producing in a 3-dimensional wind every 5 minutes. So that's used for the weather forecast, but they're using it for the weather scale analysis in real time. So as part of academia, we built up our center, and then we are working on the KMA to develop the algorithm, and also we do the research in the R2O, research to operation, and also we build up the human expert and then provide them. They also give a student to work in the KMA too. So these are some summary what we have been done with the KMA. So for the last 12 years, so there are different color. Red one is already implemented in KMA. They are in operation, and blue one is in the testing stage, and black one is a research stage. So we actually involve into the policy decisions. So what kind of radar network they want to build, where they want to put it, what kind of scanning strategy they want to do it too, what kind of data format. And also we developed a lot of different quality control algorithm to eliminate the non-meteorological echo, improve the Doppler velocity, and also we are working on the signal processing too. And of course, if you are working in the operational center, so they don't much care about the quality of radar data. So they are more focused on the operation itself. So they're working for the radar never die, but they don't much care about the accuracy of the radar data. So we actually built up a lot of the algorithm to ensure the accurate data acquisition. So we built up some different technique to calibrate the radar with the digitometer and the radar itself and ground color too. And we built up the QPE algorithm, so-called hybrid surface rainfall map and AI-based QPE. And also we are working on the nowcasting systems. So this is coming from heritage from the McGill University. So we implemented it for the weather radar as well as satellite. We are merging with a different product, and also we developing different algorithm too. And one of my colleagues also working on the radar data simulation to improve very short-term forecasting. And also we working on the radar composite, completely different concept. So they are working on too. And also CPO weather product, 3D wind that I mentioned. So this is in real time now. So they are we have 3D wind in every 5 minutes. CPO weather product, storm information, hydrometeor, and microphysics information. So we also got involved into the hardware development. So we successfully developed full phase array window profile at the 1.29 gigahertz. And currently, we are developing signal processor, working with the company too. And also, we are working on advanced product like precision tie and 0-degree height and QBP and CBP. So one thing I want to mention for the 0-degree height is basically the height of a melting layer. So we detect whether the melting layer, and then we convert them into the information on 0-degree height in the entire Korean peninsula. So basically, imagine if you do the sounding, it will give you the every 6 or 12-hour temperature profile. But the weather radar, when we have precipitation, we have a thermodynamic field every 5 minutes or 10 minutes. So now this information is the ingest into the NW model. They simulate this 0-degree height into the very short-term range forecasting system. So this was a sort of outcome of our collaboration with the KMA. So a lot of my former students actually working in KMA. So they took over all these new development and also the new algorithm development too. So now let me move on to a little bit on the precipitation microphysics that I'm interested in scientifically. So if you use a weather radar, then originally when dual polarimetry radar came out, so one of the first microphysical product was hydromedia identification or hydromedia types that was developed from the Anchor. So they come up with the first microphysical product. So still this HID hydromedia type information is commonly used to verify numerical model or predict the precipitation type at the surface too. And another, the important issue is how we can retrieve a three-dimensional drop size distribution with the weather radar data. So we are working on that. I will give a little bit of information on that. And also we are now in the stage of going for the more in detail microphysics, in particular for the cold microphysics. So with the vertical pointing and scanning radar and dual polarimetric spectral polarimetry, how we can really get the microphysical information, and then how we can quantify those microphysical information to translate into the parameterization of this microphysics into the NWP model. So as you know, most of you already went through the cloud microphysics, in the undergraduate or graduate school. So if you focus on cold microphysics, we have three major primary ice processes: vapor deposition, and rhyming, and aggregation processes. So these are complex and the primary process that control the growth of precipitation particle. And also recently there is a lot of research interest in getting the information on the secondary ice production. So these are the precipitation type identification that developed by Anchor. So you see this is RHI radar, RHI cross-section images. So reflectivity and Doppler velocity and differential reflectivity. And you see the very beautiful, the overhang cell or bounded weak echo region around here. So very strong radar reflectivity, and then nothing below there. So if you cut this area, you see the bounded weak echo. So that indication of downdraft in 5 or in 10 minutes. So that's commonly used in the operational, the weather radar system in in 1970 or 1960. But if you look at the Doppler velocity, you can clearly see that there is very strong convergence line along here. So you have a away motion and approaching motion here. So this is a strong convergence line. So along the strong convergence line, you have very strong updraft. And if you look at the GDR, so there is a GDR, high GDR in the rain. But here, when we have very strongest radar reflectivity, GDR becomes smaller. So that's indication of haze. So basically, we combine all this information to get the hydromedia information in 3D. So this is what you see here. So below you have rain and melting layer in blue, and the light blue is dry snow, and the ice crystal here, purple. And then if you look at this core area, you see a lot of hail or rain hail mixed or rhymed particle too. So this is the first product you can use. So this is a common practice for the most of operational weather radar system. And then we are working on the retrieving drop size distribution. So we started with the typical parametric approach, and then now we are approaching with the AI-based drop size distribution retriever. So I have Dr. Shin. She just got PhD. So she used all available dual parametric information to retrieve the so-called DM prime and zero prime. This DM prime is characteristic diameter. So we can interpret this one as a mean diameter. And this is number concentration, zero prime. So this is DM prime and zero prime coming from the generalized double moment scaling drop size distribution too. So if you look at the here, so you see how the detailed structure you see the DM prime in the the different cell of convective cells. And also the N0 prime, you can see how the DM actually grow from the top to all the way to the bottom, and then how N0 prime actually changes. If you look at the more detail in terms of a different stage of cumulus development, so here you see the very small storm here in reflectivity and GDR, Doppler velocity, and the retrieved DM prime and N0 prime. So here you have a new convective cell actually developing around this area, and then they grow. So maximum reflectivity and slowly maximum reflectivity become weaker. So we divide into the developing, mature, and dissipating stage. So during this period, if you look at the Doppler velocity, so here the updraft or convergence around here, it's become weaker, but the mature stage, very away motion and approaching motion become much stronger here. So associated with the strong the convergence, you see the new storm developed in this area. So if you look at the retrieved DM prime, so you have DM prime is smaller here, and then later it's much higher, like DM prime reaching to the around 3 millimeter size, and then in the dissipating stage, it become smaller size too. So if we look at this one in the following the storm cell, so what we do is we have very limited radar, but we try to follow the single cell, adjusting the scanning strategy in real time every 5 or 10 minutes. So from there, we do the Lagrangian analysis of these DM prime and N0 prime. So here we show the 3 stages. So blue one is the developing stage, and the green one is a mature stage, and the red one is dissipating stage. So and then we look at the DM prime and N0 prime, how they change with the height. So if we look at the developing stage, there are actually 2 modes. So above 1.8 kilometer, so actually the DM prime actually decrease, or on the other way, DM prime increase with the increasing height. And then the N0 prime is nearly almost constant or slightly, the increase or decrease. You don't see much change. Basically, that's indication of a condensational growth. So the upper part of a cumulus cloud, you have a very distinctive condensational growth. And then if you look at the lower layer, so DM prime actually increase, and then N0 prime decrease. So you see the conventional, the aircraft in situ measurement types, the collision coalescence growth. So cumulus in the developing stage, you clearly see the condensational growth and collision coalescence growth in the lower layer. But if you go to the mature and developing stage, now their trend is more or less similar, but the slope is quite different. So the DM prime actually increase and N0 prime decrease. So it's a collision coalescence process within the the developing or dissipating cumulus cloud. But if you look at the gradient is much stronger in the mature stage. So basically, you have a stronger collision coalescence process during the mature stage than the dissipating stage. And from there, actually, we also looking into how the actual drop size distribution change in a different stage as a function of time. This is a little bit busy image, but the color here indicate the different height. So red one is bottom part, lower area, low height, and the blue color is upper level too. And then you have developing, mature, and the dissipating stage. So in the developing stage, you see the the evolution of drop size distribution actually more like a parallel displacement. And then basically what it says is it's indicating the more distinctive condensational growth. But if you go to the mature and dissipating stage, the evolution actually controlled by this part. So you see so much increase of big drops. So again, it's indicating the collision coalescence processes. So I was talking with Pavlos, if we have a better radar system, like phase array radar, so we can do really, track the individual cell, and then we can collect the extremely high resolution, those radar data, and then now we can, apply this kind of retrieval algorithm. Then we will get the minute by minute DSD evolution information. So that can be actually used for the NWP model verification, or whether NWP model actually properly reproducing those processes too. And then if we move to the called microphysics or microphysical study with the remote sensing information. So basically the Kumjian in 2014, they were looking into so-called fingerprint of microphysics from the dual parametric weather radar system. So if you have a different primary processes, vapor deposition, aggregation, and rhyming processes, this dual parameter actually has different trend or different gradient with the height. So the vapor deposition usually reflectivity increases and KDP increases, GDR remain constant. But aggregation and rhyming they are different. Reflectivity increases due to the growth, but GDR and KDP become more like a negative, they decrease. So this is coming from 2014. And then this is an example, what you can see from the operational next radar system. So you can produce vertical profile. Although they don't do the RHI scan, what they do is the quasi-vertical profile. So you have like a 20-degree elevation angle PPI. Then you can try to combine, the average within the certain volume. Then you will get this kind of vertical profile. And then you will see the time height cross section of dual parameter variation. And then this example, you see the very distinctive radar reflectivity, so-called radar brightband. And then you see the steady growth of radar reflectivity. And differential reflectivity, you don't see much change here. And then in the lower layer, very high GDR, indicating big drops. And then if you look at the cross correlation, there is distinctive decrease of correlation coefficient, but you don't see much change in the correlation coefficient in the ice phase. So, and then differential reflectivity is similar. So you see the more or less same, and then sudden change. So again, if you combine all this information and try to match with this types of fingerprint, and then you can come up with this is mainly coming from the aggregation process. Typical, the ice process, the positional growth, and then when they become warmer, and then you see the moderate and the strong aggregation process that will produce this types of vertical profile. And then that's how they interpret the primary ice production or primary, the processes. Now I will talk a little bit about the secondary ice production. So pretty well-known secondary ice production is Harlem motion processes. So if you have random particle here, and around you have a supercooled cloud droplet, and then they collide each other, and then they start to break into the small pieces. So this is a more or less very typical secondary ice process proposed by Harland and Motion a long time ago. And then this has a special temperature range of -3 to -8 degrees Celsius. So if you have this Harlem-Motion process, this fingerprint or this dual parameter actually slightly changed now. So you see the KDP, instead KDP decreasing, KDP actually increasing. So this is sort of again, so how you can qualitatively interpret this kind of microphysical process with the vertical profile of dual parameter. And then, but if you look at the secondary ice production in the literature, then you see more processes. So I already mentioned about the Harlem motion splintering processes, and also when the particle freeze, they can fragment or small pieces into two. And another one is ice-ice collision. So you have two ice particles collide, and maybe it can split, the split into the small pieces too. And thermal shocks, when the warm particle and cold particle, the collide or collide each other, there is thermal shocks, and then ice particle will break into the small pieces. Also, sublimation-driven fragmentation is another example. If you have a virga and the ice phase, and then you have a new increase of ice particle too. And then I will talk about the three processes, three cases actually we see this kind of processes. First one is the Harlem motion process. So I've already mentioned about this process occurring -8 to -3 degrees Celsius. So this is again vertical pointing radar measurement. So this is y-axis height and x-axis time. So radar reflectivity and Doppler velocity in vertical pointing mode. And then you clearly see the radar bright band here, melting layer here. But if you look at the reflectivity, you have a certain increase of radar reflectivity in this area, and also the structure, temporal structure of radar reflectivity, more cellular structure. So that's already indicating there is a lot of updraft existing in this area too. And then one of the interesting things, why this kind of the reflectivity suddenly increase in certain height. So let's imagine this is degrees Celsius around here, and then if you go up 1 kilometer above -6.5. Okay, so this is a temperature range around -10 to 0 degrees Celsius. And then, but if you look at the Doppler velocity in vertical pointing mode, it gives more information. So imagine the typical ice crystal or aggregate, they fall very slowly because their density is very low. So usually when you look at the fall velocity or terminal vertical pointing Doppler velocity, if you neglect vertical air motion, of course, then you can get the information on whether it's a rhyming or aggregation process. So, but here, if you look at the velocity here, velocity actually somehow reach to the 4 meters per second. So imagine ice particle or snow particle drop in 3 or 4 meters per second. So because it's a dense particle, so it's a heavily rhymed particle too. So with these two information, we clearly know there is the significant rhyming process actually going on. But if you look at the power spectrum, you know a little bit more detail. So this is one single time. It's a 2022, so it's around here, around this time. And then now you have a distribution of radar reflectivity as a function of velocity. So basically, it's indicating different species of particle, okay? Or different fall velocity of particle. So let's go back to the upper layer. So fall velocity is about -2 meters per second. And then fall velocity increases and also color become brighter. It means actually particle grow. And then they become more or less constant, or the velocity somehow here you see the kink here. Velocity decrease. So I will indicate this is a very important component. So velocity actually they are steadily increasing, and then you see the drop of velocity, or their velocity become constant. And then suddenly in the right hand side, when where the velocity is smaller, that part you start to see the new peaks. So around this height, you have a double peaks. So one is a pre-existing ice particle actually falling, they grow. And then the second peak is a very low velocity. Still, we don't know this is ice or liquid, okay? But if you, and then they come down, and then they pass the 0 degrees Celsius. And then two peaks actually melt. So this one melt and this one melt too. So basically this is ice phase. So somehow around the 5 kilometer or 5.5 kilometer, you have a new generation of ice particle around this range. And then they melt even at the raindrop. So you have a two mode bimodality in a certain height here. And then they collide each other. So due to the collision coalescence process. So this is sort of indication of a secondary ice generation occurring around this layer. So this layer is a temperature range of -8 to -3 degrees Celsius. So typical Harlan motion processes temperature rate. And then I will go to the second one. So here in the literature, a lot of people says that, around this temperature range, maybe the secondary ice coming from the fragmentation or ice-ice collision processes. So I already showed many different processes. So so far, most of the dominant idea is this one. Ice-ice collision will generate a lot of secondary ice in -15, -16 degrees Celsius range. But we have a little bit different idea, different opinion on that. So here, still, if you look at the power spectrum, you have existing particle, and then suddenly around -15 degrees Celsius, you start to see the secondary peak here. And then they collide each other through the aggregation processes and become reflected, become stronger and stronger. And if you look at the power spectrum on snapshot at this height, around here, and a little bit hint of tail or the secondary peak here. But if we look at the different time period, so here you have a very distinctive secondary peak here. So you have a pre-existing peak and another secondary peak up here around -15 degrees Celsius too. And another interesting is if you look at the Doppler velocity increase here and then suddenly decrease. So this is Doppler velocity range here. So velocity decrease around 0.3 or 0.4 meter per second. And same signature occur here too. So this is a different observation. The previous one was X-band vertical pointing radar measurement. And this one is coming from W-band radar measurement during the ice pop 2018. So here, this is purely ice at the surface. So even if we look at here, you have two clear distinctive storm signature in this region. So if we look at the deep system here, so this is winter system. So you have a system up to the 10 kilometer. So during this period, if you look at the power spectrum, you have a pre-existing power spectrum here. And suddenly around this is -15, around here -15, you see the secondary peak up here, and here too. And then if you do the average for entire 1 hour, this is 1 hour average power spectrum. So even you can clearly see here too. So this is a secondary peaks you see around -15 degrees Celsius. The previous one was around -8 to -3. So it's a much colder temperature. So based on the literature, this should be the ice collision process based new generation of ice particle too. But if you look at as you see it in the fingerprint, so let's see what happened with the dual polarimeter, GDR and KDP and OHB. So you see this is the temperature range here, and you see the steady growth of radar reflectivity, and then the more or less a slight increase will remain constant. And then, but if you look at the GDR, KDP, and OHB, they showed so much variation within this range, right? From the -15 degrees Celsius. As you see here, you have GDR minimum, and then you suddenly see the increase of GDR, and they are coming back to the smaller way. So this, but if you look at KDP, so when GDR increase, KDP increases too. And then GDR start to decrease, and KDP start to decrease. If you look at the OHB has a maximum when GDR, KDP start to increase. And then they have a minimum here when the KDP and GDR become maximum. So the interpretation of this signature indicate, so you have a new particle actually coming up that should be small coming from the KDP. So it has produced a lot of ice water produced during this rate, -15 degrees Celsius. But if you look at the GDR information, that should be the more elongated, horizontally elongated particle. So we call the planar ice crystal, actually. So secondary ice, more ice actually generate around -15 degrees Celsius, and then they grow horizontally, planar types. So that's why you have a minimum rho HB, because in this layer you have pre-existing ice particle, and then you grow, ice particle in a planar types. So you have two species actually that produce very low rho HB. And then another study what we did is we actually derived the vertical air motion for the summer case. So in 17 case, so it's coming from slightly, the moderate good data set. So from there, so we collect a lot of data and then retrieve the vertical air motion for individual every minute. And then I showed as in terms of CFR images. So here, this is minus 15 degrees Celsius. And then this one is 0 meter per second. So you see in the upper top of cloud, you see the vertical air motion there. And then below there is the downdraft. And then the minus 15 degrees Celsius here, you see the signature of a vertical air motion. So below the minus 15 degrees Celsius, you have a very distinctive signature of vertical air motion. So again, the issue is, so in the literature, they are saying this ice generation was coming from the collision. So the first issue is why this temperature range was more, the favorable for the ice collision. So there is no evidence on that actually. But so what we think is there is actually the upward motion, updraft produced. So we think this is coming from the phase change from the water vapor to the ice phase. So and then that produced a lot of heating. So that heating actually produced a very small scale or the micro scale or even major scale updraft, small scale updraft. So that's indicated with this updraft motion. So if you have, let's say, updraft motion, then there is a new initiation. You have supercooled water and you have a new supersaturation, and then that will start to reactivate small ice particles. So this might be interpreted as a primary ice nucleation rather than secondary ice production. That's what we think. So in this case, we have pre-existing large particle. Actually, they grow. So in this case, so there is the positional growth as well as some rhyming indicated by the high rapid increase of fall velocity. And then suddenly new ice particle initiated and they collide each other through the aggregation and then they grow. Okay, so the process is what I want to talk about, fragmentation by turbulence. So this is one of the beautiful cases. So this is done by the Guanyin. So it's a postdoc of Pavlos. So here, so you see the radar reflectivity and bottom one is Doppler velocity. So, but here we overlay the sounding observation, wind bow there. So in the lower layer, we have easterly flow, northeasterly or easterly flow. If you go to the upper layer, there is a westerly flow. So there is a very strong directional shear. So this directional shear produces a Kelvin-Helmholtz wave in this side. So you see how the Kelvin-Helmholtz wave modifies radar reflectivity. Basically, it controls the growth processes of ice particles. And then even if you look at the vertical Doppler velocity, you see the up, down, the very wavy structure that produces the systematic down and updraft motion there too. The issue is what will be the main role in terms of ice growth or ice processing. Okay, so this is two way of we are looking at these processes. One is we have a vertical pointing radar in a single location we are looking into, and then it will give you radar reflectivity and Doppler velocity, and also from the power spectrum we can get the spectral risk, unison, and cortices. So this is a vertical pointing information. And then also we are overlooking towards the super side. We do the RHI scan that will give you horizontal, the information, vertical information of dual parametric parameter in K-band. This was a NASA Israel radar was participating our ICEPOP 2018 International Field Experiment. So here you see the Kelvin-Helmholtz wave here. So this Kelvin-Helmholtz wave is actually slightly different to this one. So this one has a Kelvin-Helmholtz wave produced by the directional shear. But this one, we had the same wind direction, but we had a very strong speed shear. So we have KH waves produced by a speed shear in this case. And then if you look at spectral width, very high spectral width occur around here. And then clearly above and below the Kelvin-Helmholtz wave, you see the skewness actually change, negative and positive too. So and if you look at the dual parametric parameter, reflectivity increases, and then GDR, KDP also increases too, but rho HB decreases. So imagine those cases in around minus 15 degrees Celsius, you see the GDR, KDP increases, rho HB become minimum later, and reflectivity increases, same signature too. So if you look at the power spectrum for this case, so now here in the bottom figure, we see the two different heights. Just the one height is just where the Kelvin-Helmholtz occur, and then this one is below the Kelvin-Helmholtz waves. So we have before the Kelvin-Helmholtz wave occurs, so we have a power spectrum. So we have this kind of a little bit of a signature there. There is a slight, very light Kelvin-Helmholtz wave there. But during the Kelvin-Helmholtz wave at the height here, so you see the spread of a power spectrum. So it goes to the left and right, plus and minus, they are almost near symmetric. So it's an indication of wave feature. And then if you go to the lower layer later, after Kelvin-Helmholtz occur, so let's say we have Kelvin-Helmholtz occur above, and then there's a lot of processes going on there, and then we try to see the below. And then what will be the outcome of this Kelvin-Helmholtz waves? So after Kelvin-Helmholtz waves, you clearly see that this second peak become more dominant. So you have a pre-existing particle and then new ice actually produced. So we think this is like a wave or turbulence produced breakup processes. So it produced a lot of secondary ice. And then now I will go back to the different case. So I mentioned about Kelvin-Helmholtz wave and also the two processes at the Harlem-Mosher and also minus 15 degrees Celsius. First, let's look at again for the minus 15 degrees Celsius. So this is the radar reflectivity, and this is the spectral width. So you see the rapid growth of radar reflectivity here around this lane, and then here spectral width become much broader. So this increase of radar reflectivity is linked with the broadening of a power spectrum. And then during this period, actually what we did, we followed the trail. We followed the trail, and then we draw the power spectrum. So this is how it looks like. So we have a pre-existing particle, and then around this side where around 4 kilometers, where spectral width become broader and the reflectivity increases, and then you see the second peak there too. So this is minus 15 degrees Celsius. So in this range, so minus 15 degrees Celsius range, we start to have a secondary peak there. And then what we did is we tried to separate this peak and this peak. So we tried to fit two Gaussian into the primary peak and secondary peak. And then we recalculate the radar reflectivity from the secondary and primary peaks. So this radar reflectivity coming from the secondary peaks. So we have a fall velocity too. So secondary peaks start around minus 50 degrees Celsius or a little bit colder temperature, and reflectivity increase toward the lower level. So you see this ice particle, secondary peaks, new generate ice particle actually start to grow from the minus 15 to all the way to the minus 12. And then they disappear, they collide each other with the pre-existing particle. So you see the aggregation there going on around that height. And then in this case, we have a very typical fingerprint of a dual parametric parameter. So you see this is coming from the three peaks. One is full spectrum, and second green one is fast mode, primary peak, and this one is slow mode, secondary peaks. So if you look at the secondary peaks, you have a steady, rapid growth of secondary radar reflectivity. And then if you look at GDR, OHB, and KDP, GDR and KDP has a maximum, and OHB has a minimum. So it's perfectly matched with those fingerprint I already mentioned. So this is what we call the simple case, very simple. So we already know what's going on there. And then let's go a little bit complicated case. So upper one you already saw, so that's a simple case. And the bottom one is a new case now. So again, around 5 kilometers. So you see the increase of reflectivity, spectral width become much broader. Same signature at minus 15 degrees Celsius. So this one is the same as what you see here. And then reflectivity decrease between 3 and 4 kilometers. And spectral width become narrower. And then suddenly around 3 kilometers, we have the same signature. Reflectivity increase, spectral width become much broader. So what it is here. So this is power spectrum along this trail. So we have a pre-existing particle here. And suddenly around minus 15 degrees Celsius, we start to see the secondary peaks. But in this case, secondary peaks actually took over primary peaks. So the growth of this one is more dominant. And then, as I did before, so what we separate and then try to see what's happening with the slow mode. So how the reflectivity in slow mode, small particle here, this one and this one. So here, this is a minus 5 degrees Celsius temperature range. So pre-existing, two modes actually collide each other around this layer and then become single peaks. And then minus 5 degrees Celsius, you start to see new secondary ice, new mode at the small fall velocity occur. So imagine that was the first one, Harlem motion process. So this is the case I would consider two ice generation processes occurring. One is minus 15 degrees Celsius, and the other one is a typical Harlem motion process. So in this case, again, since Harlem motion process exists, so we can expect that very strong updraft. So that produces a lot of supercooled water. Then in this case, second peak, actually, this one, new ice particle generated by Harlem motion actually overcome entire snow growth in this case. So again, we don't know exactly why. Why in this case? In this case, previous one is this one primary was dominant, but in this case we have this second mode or slow mode or new generation of particle take over entire snow process in this case. Okay, in this case we have a similar signature. So we have maximum here, and the minimum GDR OHB here too. So this was typical signature as same as here. But if you look at the Harlem motion, that's slightly different. So what you see here, GDR and OHB, they have similar signature at the minus 15 degrees Celsius processes. So maximum GDR and minimum OHB. But now the KDP maximum location is completely different. So you see this maximum could much higher or hold temperature. So this might be the indication of the new supercooled water exists. So the new supercooled water actually produced a lot due to the strong updraft in the upper layer, and that initiates the Harlem motion process in the lower layer. But we don't know exactly what's happening in that height too. Okay, so I went through some overview of what we have been done for the last 12 years with KMA, and also we slowly going to how we can utilize dual parametric radar data in study on the very detailed microphysics study. So the next step, what we are actually looking into is we want to quantify this information, because most of in situ measurement has very limited sampling, so you don't have a sufficient information. So we can identify that this microphysical processes or secondary processes with in situ measurement. But in the end, we try to match this in situ measurement with this radar measurement to have a massively produced quantitative information to somehow interpret that information into the numerical parameterization of microphysics in NWP model. I think that's all for me.
Thank you, Gyuwon, for the journey to ice microphysics through the lenses of a radar. And takes an expert to see all these details in as was demonstrated. We have time for a couple questions. Ed?
Very nice talk. So my understanding is that you mentioned sublimation fragmentation is one of the SIP processes. So Alexei Korolev has said, well, he questions not that it exists, but that it's important because, well, if it's sublimating, then it's in an environment that's not gonna. What is your? Do you have an opinion on that?
Yes. So we are looking into those processes. We have a lot of the vertical pointing measurement where you have those the anvil actually comes up, and then they slightly the height of anvil actually coming down. So during those cases, you see a lot of sublimation. So you have updraft and there. So we clearly know that there is a sublimation process actually existing there too. So we are looking into the how actually we can get the double bimodality in that such cases. So but except for that, the sublimation is mixed within the those entire deep system. It might be very hard to figure out those clear secondary ice process layers.
Thanks.
Dan and then Jane. Go ahead.
Yeah, I had a similar comment to the study of the Karlsruhe folks, Alexei Kiselev, and principal in AGU, he said the laboratory experiments buried the Hallet Mossad. And I was always skeptical about Hallet Mossad too, but maybe the kinetic regime of the collision or so, what we do in the lab, is not the same as in the cloud. And I'm wondering if you could use your data, not necessarily looking that it happens, but indeed with turbulence and size, give energy estimations. Or Vaughan Phillips tries to do it really with kinetic parameters. I know the Manchester people tried to simulate Hallet Mossad years ago, never published. They didn't find evidence for that. Now the Karlsruhe guys don't find evidence for that. But it doesn't mean it doesn't exist. It's maybe really a different kinetic regime. So would be interesting maybe if data or long time data has radar data could help to constrain the kinetic regime. That's more a comment.
Okay.
My other question, what I try to understand, one of your, not the last case, but before where you started showing this little peak on the right-hand side, you said it's super cool. Yeah, the case study before this one, where you said there's liquid, I think here somewhere, there's liquid droplets updrafting coming up. You said something there.
Yeah.
So is that, and then you mentioned that maybe primary even, so.
Oh, well, this one is secondary.
Okay, it's
So,
secondary.
so
I try to follow your
Yeah.
concept.
right.
Maybe you could elaborate once more.
So here, definitely there is one limitation with this measurement. First, we didn't have a sufficient sensitivity to get another species of particle. Because to produce this kind of process, definitely we need to have supercooled water or supercooled droplet. But because we know that this one, second peak is ice already.
Okay.
Because it's melting in this side. So we clearly know this is ice and this is ice. So where is a liquid?
Okay.
So I think it's a limitation of our instrument. There is somewhere in the right-hand side or similar range we have supercooled water there.
Yeah, so there's not a problem. I'm not a radar person, obviously. There's no problem of extinction of the signal.
No,
That
no, not
okay,
this one.
okay, so it's really somewhere else.
I think he has a better radar than me, so we'll find it, you know.
He said it, it's a sensitivity. He can't see the super cool liquid.
Yeah, okay, it's sensitive, not extinction sensitive.
Yeah.
I think you share a lot of exciting results, kind of dealing with this complicated signals, right? So now the PMA has an aircraft.
Yeah.
Right, so do you plan to do any
Yeah.
campaign,
Yeah,
try to
okay.
get some in-state data
Yeah.
supporting your stuff?
Yeah, I didn't mention about our new field experiment. So some of these data actually come from the international field experiment we had during the Winter Olympic Games in 2020, 2018. So we have a major field experiment during that period. But the problem was KMA, King Air, wasn't flying much because they are also afraid of going inside cloud, although they have very good microphysics probe. So now they actually installed the K-band dual parameter radar in the aircraft, and also they have a better in situ measurement now. So hopefully, when we have the new field experiment in 2026, we call the KPOP, Korea Field Observation Program. So this is again multi-year international field experiment. So our King Air will fly. So last week I was in Toronto to recruit NRC Conway to fly for this experiment. So we'll see what's happening.
All right, very good. I think that will be all. I don't know if we can check if there's any question from the chat. Okay. Well, once again, join me to thank you only on this presentation.